Hello, my name is Sasha, and I am going to be presenting on my group's final project for the CS Machine Learning class at UVA. And I did this project with my friends and colleagues, Malik Kurtz and Rajiv Koliwad. And essentially, our project is implementing auto differentiation. Auto differentiation is one of a number of different forms of calculating derivatives of a function computationally. There's symbolic differentiation, numeric differentiation, and others. And each of these methods have various trade-offs in terms of the accuracy of the output, the computational cost of calculating the output, and also the flexibility of the code. So if you're calculating derivative for a new function, to what extent do you have to hard code in things? To what extent can you reuse code? And automatic differentiation does a pretty good job of balancing these different trade-offs. And for that reason, auto differentiation is sort of the way in industry a lot of the backpropagation is done for neural networks. And that's why we're doing this project for this class. The code we created does work for calculating just the derivatives of functions, but it also works for backpropagation for neural networks. So without further ado, I am going to go ahead and give a little demonstration of how auto differentiation works. I'm not going to do it for a neural network right now. I am just going to do it for a function. But pay attention because if you're familiar with neural networks and MLPs, you'll sort of see how it's analogous. And then after I do that, I'm going to go through the code and talk about some of our conclusions. So here's an example. We have a function where the inputs are x and y, and the output is xy plus e to the xy. We're going to evaluate it at a certain point when x is 1 and x is 2. Now, think about an MLP. When you're performing backpropagation during testing, you're putting in your inputs. Here's our inputs, x equals 1, y equals 2, and you're going to get an output. And then you're going to find the derivative and use it to sort of work backwards and then eventually tweak the weights and biases so that you get a more accurate model. So we do this setup here with these nodes. You can kind of see we're going to rename x and y, x1 and x2. And then at each step, we're going to create a new node as we're sort of building our function. And every node needs to have two inputs. So we'll move on to the next slide. Yeah. So first we generate a forward trace. Note we're doing like backwards automatic differentiation. So rather than just going through and calculating the derivative, we still need to sort of go through and get some information, and then we work backwards. So we have the trace, that's like each node we're looking at. And then we have our function, which is like, what is this node in terms of what comes directly before it? After we get the function, we calculate the actual value at the points that we're looking at for each. And finally, what we do is we calculate the derivatives of the given like node or trace with respect to what comes before it. And sometimes these derivatives are going to end up being constants, like in the case of the derivatives of x1 and x2, but in other cases, they're not going to be. For example, like in the case of v2. So we generate our forward trace, and then we start the reverse pass, and we work backwards. And we set the partial derivative with respect to the final node as 1, because v3, that's kind of already our function, and then that's going to be our f of x and y. So we set that as 1, and we work backwards. So we're going to start off here by going to find the derivative of v2. Now, if you remember the chain rule, basically says that if you have like the derivative of A over C, that's equivalent to the derivative of A over B times B over C. That's essentially what we're going to do here. We have the derivative of the final function with respect to V3, that's just 1, and we have the derivative of V3 with respect to V2, which is also just 1. So we use the chain rule to multiply those together and we get 1. Next, we are going to go to V1. Now, V1 has two child nodes. So what we actually have to do is we have to add those together. And the derivative of V1 is going to be the derivative or excuse me, the derivative of the function with respect to v1 is going to be the derivative of the function over the derivative of v3, which is 1, over the derivative of v3 with respect to v1, which is also 1. And I'm just going to go back here. So if you have v3 here, and its arguments are v1 and v2, we calculated that the derivative of the first argument, or with respect to the first argument, v3 over v1 is just 1. And so that's what we're doing here, by the way. We're using these values that we already calculated during the forward pass. So I'll go back here. Yeah, we have 1 times 1, and then we have to add that with the derivative of f with respect to v1, which is equivalent to derivative of f with respect to v2 times derivative of v2 with respect to v1. And that's going to be 1 times e squared. And I'm going to go back again just to make sure you get that. We have v2 over v1. The derivative of the first argument is going to be e to the v1. But because v1 was already calculated to be the value of 2, we plug in the value of 2 to v1, and we get e to the squared. So now we're here, and we have our output 1 plus e squared. We're going to keep going. We're going to do the same for x2 and x1. Same process. We get for derivative of x2, 1 plus e squared, and for x1, 2 plus e squared. And now we have our derivatives. That's basically how auto differentiation works. I'm not going to go through an example with MLPs because that would be a lot more complicated and I want to have time to go through our code base. But now I'm going to shift gears and I'm going to show you our code with this in mind and how it performs backpropagation. So I'm going to swap over to that. And here's our code. And so me and Malik and Rajiv put this together. Now, credit where it's due. Malik did probably do the most work on this, and he deserves credit for it. But we all put in some work. And then with our division of labor, I get to do the presentation. So, and I like to hear myself talk, so it's perfect. So I'm going to start off with this tensor class right here. And if you scroll up, we just have some imports of things we need. Like we use NumPy arrays as sort of our base. If you see in the, where is it? In our gradient descent, just like our main file, we import the sklearn.model selection train test split because that helps us train our model. So pretty standard stuff. We have some, oops. We have some debug options for configuration and just makes it easier to figure out what's going on in the code. So we start off with this tensor class, and this is an incredibly long file, but it's essentially the heart of our code here. And a tensor represents a given 2D weight matrix for a layer, or maybe a given 1D matrix for, a 2D weight matrix for layer, or a 1D bias matrix for layer. We also have some important data like what's the shape of it? Does it require a gradient? And some unfilled variables that will later get filled when we actually run this code. And before I go on in explaining the tensor class, I think it would be helpful to go over the classes that will contain it. This is our layer class. It represents the layer of an MLP, excuse me, and it's going to contain 2 tensors, a weight and bias tensor, as well as an activation function. Then that will in turn be contained by the neural network class, which contains a number of layers and features a forward function, which will use the layers and tensors within to calculate an output tensor from the input tensor. Just like how in backpropagation, you have to go forward and then you have to go back, just like what we do in reverse automatic differentiation. Then I'll go to our GD file, and this is essentially our main file. We have some basic setup of an MLP, which I'm just going to skip over for now. And then finally, we get to our training loop. And you'll see we go forward in our neural network instance to get an output. And I'll talk a little bit more about that when I get to the tensor file, but we also have different functions in our tensor class that do things like add, multiplication, activation functions, but I'm going to go over that in a little bit. Um, and then we use a function, where is it, to calculate our loss. That's cost Fn. And then we're going to perform the backward pass right here. And this will calculate the gradients for all the tensors except for the input. And by the way, this function right here does return a tensor. And we coded tensors to use the same basic operations as NumPy arrays. So let's find that backward function, returning to our tensor class. So here's our backwards function. And essentially, it's going to do a post-order DFS search on the nodes that we have in our MLP. And then it's going to go through a reverse topological order and call it and calculate the different derivatives for different nodes. And let's see. Yeah, this is just kind of necessary for the computer just so it knows which order to go through things and also make sure that everything's going to have 0, 1, or 2 children. And then finally, we go in reverse topological order, as I was saying, and we call tensor dot underscore backward. It's different than just tensor backward. So I'm going to scroll down, and what you'll see is you'll see all these functions define add, sub, multiplication, and even if you go way down, you'll see things like sine, cosine. We have different activation functions, and essentially, these functions were all being called during the forward pass when we were calculating our output. But you'll see within each of these, they have another function defined, and that's that underscore backwards function. So each of these functions, depending on what was happening then in the MLP for that node, one of these functions was actually called during the forward pass. And when it was called, we had the underscore backward function set depending on which one of these was called. So each one has a separate definition for what the actual backward function is going to look like. So let's take a look at the sigmoid function, for example. So during forward propagation, we used sigmoid to calculate the child values, and then we stored it in this backward function. We chose it. And then during backpropagation, the backward function is going to be called for the given tensor when it's its turn in the reverse topological sort. And that's when we're going to calculate that gradient. And you'll see for calculating that gradient, this is actually an application of the chain rule. And we have to use this because remember that we're dealing with a tensor for a entire like set of weights or set of biases for a certain layer. So that's a lot of different nodes going on. So we're going to apply that. And in this example, we're using the chain rule to calculate or add to the parent gradient, and you have the child gradient times the child data times 1 minus the child data. Why is that? Well, if you go up here, we have child data, that's our sigmoid function, and the derivative of sigmoid is actually sigmoid times 1 minus sigmoid. So it's kind of perfect, and we can write a little bit clearer to understand that code. And we already, yeah, so then it's convenient, and I'm going to return to our GD file. So once that backwards pass has been performed and we've stored all the different gradients in the different places in the function, then we finally take that GD step. And we go through and we adjust all the weights and biases using their appropriate gradients. And the strength of this adjustment, as in MLP, is determined by the learning rate, which is one of our preset configurations. And finally, we can now use the testing data. And we throw it through, but this time we're not calculating gradients, and we calculate loss, and we can get our output. So I am not going to run the version of it I have here because we basically did a slightly overkill example. We just used it for basic linear regression. It took like hundreds of epochs. I'm not going to do that. So rather, what I'm going to do is I'm going to show some of our other things that we did. So the first data set we used is we tested the approximation of a sine function, and we got a pretty good prediction with it. And another thing we did is use something else, which was, nope, we don't want that. Where are we here? Oh, yeah, we do want this. And then we compared it with a PyTorch model of the same architecture. And I'll talk a little bit more about some of the conclusions we had, but as you can see, ours is kind of pretty similar. Another data set we used was predicting housing prices in Boston based off 13 different variables. And again, we got it pretty accurate with this. And yeah, this is it compared with the PyTorch model. And what you'll see in, I think this is pretty impressive and pretty cool with what we did, is that the error of our different different things we modeled wasn't that different from the PyTorch. On average, PyTorch is like a tiny bit better. Um, like in this example, yeah, okay, PyTorch had a better mean absolute error. The max error was actually worse for PyTorch. Or in this example, PyTorch actually had slightly higher mean error. But what you'll see for all of these examples is that the PyTorch runtime was twice as big. So we actually got it down to like half as much time. And I guess the conclusion would be that, well, probably this is because PyTorch has all sorts of optimizations that are going to work for like much more complicated models. And I wouldn't be surprised if we made a much more complicated model, PyTorch outperformed us. But interestingly enough, for these like simpler MLPs, we get the same accuracy as PyTorch for half the time. So, in conclusion, I think the project was quite successful, and I had a really fun time doing it and learned a lot. So, thanks Malik and Rajiv for working on this with me. Also, this was Malik's original idea. He was the one who proposed that we do auto differentiation for machine learning, and I'm glad we did it. So, thanks for your idea, Malik. I also want to say thanks, Professor Chi and all the TAs, for letting us do this project, for teaching the course material in this class. I came into this class with like zero knowledge whatsoever about machine learning. So I'm a long way from that. Now, I probably might want to add to this project further because it's fun. There's a lot more we could do. Whether that's implementing other techniques that are used in MLPs in like our own way and integrating it in with what we already have. That could be also adding more to the tensor class, adding like different activation functions, other operations and things like that. And probably also going through and refactoring so that our code follows like good coding practice a little bit better. Because, if we're going to keep adding stuff and make it bigger, that starts to get more and more important. Um, yeah, I had a really good time with this project. So thanks for watching this video, and I hope you enjoyed. Bye bye.